right, so let's get a good example in, get some practice in. When should we recognize free radicals out in the wild? How do we know we're going to be working with something that has an unpaired number of electrons? Well, a really good first example is by drawing the structure of the molecule nitrogen monoxide, or NO. There are two stables at first that kind of become apparent that they may be structures for nitrogen monoxide. However, by using the formal charge method that we just learned by observing the formal charges in this hypothetical case, we can determine which, if either, of these two structures is going to end up being the most stable. All right, so try drawing the structure of nitrogen monoxide. Use formal charges to determine which structure is going to be the most stable, and then we can compare our answers. All right, welcome back. Let's use the method that we've already learned, right? Just because we're finding exceptions to the octet rule doesn't mean we are going to entirely throw out our rules for drawing Lewis structures. We are still going to be following those rules, just now we can use formal charge as almost like a hidden rule number 9 to determine when it's okay to not actually have a complete octet. All right, so our radical nitrogen monoxide is going to have a total number of valence electrons equal to 5 from the nitrogen plus 6 from the oxygen, giving us a total of 11 valence electrons. And here we can already see, before we start drawing the Lewis structure, we have an odd number. This means that there will be an unpaired electron somewhere. Our electrons are more stable when paired, but in this case, we are going to be working with a free radical. Something is going to be 1 electron short. As we start drawing the structure for nitrogen monoxide, we can see the skeletal structure here. We don't really have one atom in the center, rather the two are just bonded to each other. We have currently used 2 electrons from the pool, meaning that there are still 9 electrons left to place. Which of these 2 counts, though, as like the terminal atom? Well, let's pretend that it doesn't matter, because it really doesn't. There is no central atom. Again, they're both in a partnership. And O. So let's say in one case, we're going to start adding our 9 electrons, or we're going to start by adding them on the nitrogen and then move to oxygen. In the other case, we'll start with oxygen and then move to nitrogen. So there are 2, 4, 6, 8, 9 electrons that can be placed, and here we see oxygen now is left with, or it's left hanging with an unpaired electron. Or in the right-hand case, 2, 4, 6, 8, 9, and it's nitrogen that's left with an unpaired electron. So there are 2 different options here, and we can build off of either of these options, and that's perfectly valid for now. We're going to observe formal charge once we are finished trying to satisfy the octets as best as we can. Currently, in our structure on the left, our nitrogen has 8 valence electrons, and the oxygen has 2, 4, 5 valence electrons. Well, we're not going to get to a total of 8 on both sides, but we should try to get as close as we can. So we're going to take a lone pair from the nitrogen, move it into the center. This gives us still 2, 4, 6, 8 electrons on the nitrogen, 2, 4, 6, 7 electrons on the oxygen. And this is as close as we can get to 8 without going over. Similarly, with the structure on the right, the nitrogen only has 5 electrons around it, so we're going to take a lone pair from the oxygen and move it in towards the center. This means that now we have 2, 4, 6, 8 electrons on the oxygen and 2, 4, 6, 7 electrons on the nitrogen. Currently, we are as close as we can get to satisfying all of the octets, but we have 2 unique structures. One, with the free radical electron present on the oxygen and the nitrogen being satisfied. I'm just cleaning up the structures here. And the other, where the free radical is on the nitrogen and it's the oxygen that's perfectly satisfied. So let's determine what the formal charges are to really double check which of these 2 options is going to be the best option for the molecule. All right, well, nitrogen normally has 5 valence electrons, and we're just going to follow the same method that we've used before in our previous example. There are 1, 2, 3, 4 lone pair electrons, and we're going to add that to 1/2 of the bonding electrons, which is a total of 2, 4. This gives our nitrogen a total of a -1 charge, right? We're taking 5 and we're subtracting out a total of 6. In here, algebraically, this gives us a total of -1. The oxygen with the unpaired electron normally has 6 valence electrons. It currently has 3 electrons in the form of lone pairs, and there are also 4 electrons around it in the terms of a chemical bond. This means that the formal charge on our oxygen in the structure on the left is a +1. So these two will cancel each other out across the whole molecule, which matches our nitrogen monoxide not having a charge. However, we can see that between the two options here, the oxygen and the nitrogen both have formal charges independently. If the other structure has formal charges equal to 0, we know that it is going to be the more stable option. So let's check it out. Our nitrogen, same thing, same process, 5 valence electrons. We're going to subtract out the 1, 2, 3 lone pair electrons and 1/2 of all of the bonding electrons, which there are 4 here present. This gives our nitrogen now a formal charge of 5 minus 5, which is equal to 0. And our oxygen, with its 6 normal valence electrons, currently surrounded by 4 lone pairs and 1/2 of 4 bonding pairs, also has a formal charge equal to 0. So despite the fact that nitrogen has an unpaired electron right here, this unpaired electron actually gives it a formal charge of 0. So although nitrogen's octet is not satisfied, this is as close as we can get, and our consolation is that this nitrogen in this form actually has the perfect balance between bonding pairs and lone pairs and enables it to be perfectly satisfied, or at least satisfied enough.